is Andrew Campbell of the Tennessee Valley Authority, commonly called TVA. And his presentation is a project showcase of the Infinity 2 project, which is a collaboration between TVA and Type 1 Energy to build the U.S.'s first commercial stellarator fusion, did I say that right? Stellarator fusion power plant. Some fascinating content, you won't want to miss it. And so I'm going to welcome Andrew to the stage, and then we'll take some Q&A following his presentation. Andrew, come ahead and be with us, and thanks for coming out.
Thank you. All right. Let's see. Does it work? Okay, it works. So this is going to be more than just the Infinity 2 project because, quite frankly, none of this fusion stuff exists yet. It's all brand new. We're still designing it. There's physics papers that say it should work, but until it actually does, we're here with developing and moving it forward. Oh, I've got a bunch of notes here because there's numbers because I'm an engineer. I'm going to talk about them, but I don't want to get them wrong. TVA, we're going to cover who we are first because we're a little different. This is FDR signing the TVA Act. We were founded in 1933 as a federal agency to uplift the entire Tennessee Valley region. I've got the note here, so to improve the navigability and to provide for the flood control of the Tennessee River. So there's a big river that you'll see in some of these slides later that runs through our whole territory that was an absolute nightmare when it rained. We had massive flooding, huge economic issues with all of the regional cities. To provide for reforestation and proper use of marginal lands in the Tennessee Valley, provide for agricultural and industrial development, and to provide for national defense and for other purposes. So a lot of that does not sound like an electric utility that we look like today. So it's a slightly different mission. So these are our missions, the 3 E's: energy, environment, economic development. Energy is really what you see us in the news for today, but supporting that energy for the people of our valley, that's where the natural resource stewardship, managing the river. My very first role at TVA was 2004 as an intern. Watched out for the fish. How much oxygen's in the water coming out of our dams? How warm is it? How much runoff from our coal plants is escaping any of the ponds? How do we control that? How do we treat that? So really stewarding the valley's natural resources, preserving them for future generations is important to us. And then partnering for economic growth. 1930s, Great Depression, the Tennessee Valley region was among the poorest in the country. Absolutely, very little industry here, very little going on. How do we uplift that and make it, an attractive area? And if you look at recent data, where new factories getting announced, new processes, new, people moving into the Tennessee. It's a lot of change over the last, 90 plus years that we've been around. Who loves, World War II era imagery, right? This was our integrated resource plan, the old 1930s. It looks great, but it lists all those things. So there on the left, you've got navigation, electricity, economic equipment and improvement, land, agriculture, all of them coming together for an integrated, let's use all the resources together. And this all builds towards why fusion today. We've always been just a little bit different on how we view technology and the resources of a region. Now, the really interesting one there, you see the nitrate facility, the nitrate works on the right. That is one of the very early developments of a large government project. It was built it wrapped up right at the end of World War I, but nitrate, anybody know what nitrate's used for? TNT. There you go, TNT. War effort, TNT, that's a lot of the reason that national defense comes together. Really what we had there, was something close to Haber-Bosch technology, which is a ammonia generator. The Germans developed in the, I think 1909 or something was when Haber-Bosch came about. But in Muscle Shoals, the International Fertilizer Development Center is one of those things that TVA worked with very early. We developed a lot of the modern fertilizer technology that fixed nitrogen from the atmosphere to raise crops and move about, how you feed populations greater than we could then. You get better crop yields, improved it. That was one of our, technological innovation improvements. Still there today, a lot of that. We don't quite produce fertilizer like we did. It's all commercialized and private now, but the technology development happened there. This is our region, 7 states. So you see all of Tennessee, quite a bit of Mississippi, a little less Alabama, a little less of Georgia. You got the western-ish part of North Carolina, corner of Virginia, southwest Kentucky. That's the power service area in dark blue and the watershed for the Tennessee River in light blue. So that's kind of who we are. If you look real close at that tiny script at the top that says 2012, our fence of the service area and obviously the watershed does not really change over time. Those are 2 things that are constant for us. The population is the only thing on that slide that's probably an out-of-date number. I hear 10 is on a lot of our current stuff, maybe 11 million residents compared to the 9 there. So a lot of growth, somewhere between 10 and 11 today. But that's who we are, and then all the square miles and drainage areas and parts of the river. And we are expanding our energy supply. These are some of those numbers I want to get right. Each of the past 2 years, this is 26, so this slightly, we didn't quite hit a peak this year, but 24 and 25, we hit new generation peaks for our region. 35,430 megawatts was our January 25 all-time peak. So, 35 gigawatts, we're a pretty large utility as far as what we're serving. That was 2% higher than the previous record peak. So over time, it's been a lot of electric growth in the years. When I started, it was, up there a little bit, but we had something called USEC in Kentucky that did uranium processing. It was a gigawatt plus by itself. But we're back to those levels now with just population and industry. So meeting growing demand, we're making significant investments. Where's the number? 22 billion in the past decade, 4 billion in 2024 alone. 16 billion in current planning assumptions for power generation expansion projects. So a lot of growth coming up in the power sector. A lot of that's the AI he was talking about. It takes a lot of power. I was at an event just before the holidays where I heard Georgia Power's chief speak. She said they were coming up with 20 gigawatts of new generation, and one of their plans was what they had looked at proposing to their utility commissions. They're about a 30 gigawatt system, so it's a huge amount of growth. We'll get to the next slide. It's got all the little, I went backwards. Didn't know I could do that. Here's where all that power is. So green ones are new generation, orange ones are under construction, blue ones are planned. So new generation, Paradise, Colbert, those are going to be combustion turbine frame units we've put in recently. Johnsonville's got some aeroderivatives. All the currently building Kingston, plant near and dear to my heart. It's 38 miles from my house in Knoxville. I don't know how far it is from downtown. But I was engineering operations manager there. It's a 1954 9-unit pulverized coal plant. That is currently getting a combined cycle gas plant and aeroderivatives, and the coal units are still there right now. It's going to be the Kingston Energy Complex. It's also very close to Bull Run, about 15 miles from where Bull Run sits, same region. So there in the east is where those plants are. Cumberland City is kind of in the north central portion of the state. They're getting a combined cycle asset as well. We've got some batteries there. Those are going to be important. We've got the Memphis, Allen's getting some aeroderivative combustion turbines at the side of the coal plant that was there. So this is a lot of energy expansion, right? So when a lot of us started, I was early aughts. We had 59 coal units, We kept about even on generation, but changed out for some gas units over the years. Maybe a slight decline in that decade of very flat growth for a lot of people. And now we're back into the energy is increasing year over year. All right, now we're going to get old again. Bull Run site. You can tell it was the 60s, right? This is how drawings looked then. But some of the really interesting parts of this diagram and the plan that we were integrating and all the resources at once, look at the future reservoir noted below. There wasn't even a lake there for cooling water when they started planning sites. There's a bridge drawn in, so there was no roads. L&N main lines, spur lines, all that stuff's infrastructure, right? And it's going to be a theme on why some of these retired coal sites are so very interesting for long-term energy development. Previous slide, I talked about all the coal plant sites that now have gas. There's a lot of advantages when you've got rail spurs, you've got river access, you've got grid connections, power lines, right? Those are all very expensive infrastructure items that you probably don't have to rebuild. You can reuse them. I worked at the Bull Run site. If you look at the kind of the plant scratch out, between that plant and where that rail spur is, we built an SO2 scrubber in roughly 07, 08, and 09. So that was my first kind of boots in the mud construction field job all those years ago. It is now a level flat bit of gravel again because we've done demolition on that site. If you want to see the stacks fall, it's all over our social media. It's just Bull Run stack demolition. It's always an impressive video. We have pretty good drone footage of that one. But you know, those improvements are important. What you can't see in a picture like this, what else is in that area? If you take Edgemore Road, drive down just a little bit, you'll get to a reservation that's got guard shacks, you know, guys with ARs and they want to see your ID. We used in the 1940s in East Tennessee. Oak Ridge National Lab sits literally just down the road from Bull Run. They have a fusion directorate, they're good with energy, did a few things with atoms in the 40s that were important. So that's there. University of Tennessee Knoxville's got a great nuclear engineering program because proximity to the lab. They've got a fusion part. They've been around since forever, right? 1790s. They're over 200 years the university's been in Knoxville. So we've got that. We've got TVA as, you know, willing federal agency / utility in the same part. And we've got state leadership actively involved in, you know, the nuclear renaissance in the US. If you look up all the press releases recently, we have fuel processing, traditional fusion, generation 4 reactors, advanced generation 3 reactors, new fuel development types, and nuclear fusion options all existing in the same region together. So, I mean, everyone always says the Silicon Valley of this or that, and it, you know, kind of doesn't happen. Well, this is just where nuclear stuff happens and has for a very long time. We're very familiar and very comfortable with it, and you know, we like to see that expand and grow, and having all those different actors support at the same time really helps. Here's the engineer in me. I cannot resist an isometric turbine drawing. This is what Bull Run was, 889 megawatts. Weird side mount condensers. I've never seen them anywhere else that I've worked. I've been to quite a few power plants in my career. But I did a little math. 889 megawatts, that's almost 1.2 million horsepower around them. That's a big machine. And that's important because of that infrastructure we talked about. Turbine building's got bridge cranes that are 150 tons each. There's 2 of them. So turns out fusion devices that we're looking at weigh a lot, and it'd be good not to have to build new bridge cranes if you can avoid that. We already talked about roads and infrastructure, grid connections, but really these sites have all of this structure that's not tied to just the turbine. Could be hugely important long term for how you can actively demonstrate new technologies without building all the extras and paying for it, so you can be really useful with limited research funds and push things forward. This is one of those things. So on the right, and we'll get a little bit there later, is generator rotor. Heavy, very hard to pull, but you know, they got the crane right there. Getting the permits for the roads was actually probably a bigger issue than anything else. But we're not going to get rid of that generator rotor right now. We're going to actually put in place one of our first synchronous condensers. There's power, and then there's power. It sounds a little weird, but inertia on the grid is really important. So big spinning masses, if anyone's ever felt like a air conditioner kick on and lights dim, that's kind of the inertial part of power. It's where you don't have quite the right, reactive power on the grid. So renewables, lighter weight, new generators, things like that, they've got less megabars. And you can generate bars with sync condenser. Basically, we're going to put that guy on grid, swap the leads, turn the generator into a motor, spin it, but we can do a lot of grid services with that same equipment because I've got now spinning mass. We can put a field on it. We can do all those sorts of things with that. On the left is when we were unloading the stator half, originally from the crane, so same stuff, same turbine hall. All these years later, we can still continue that mission at Bull Run and another energy complex. So we'll have grid services in addition to all our fusion work. All right. I'm a mechanical guy, not a plasma physicist. So this is very much going to have slides from our partner Type 1 Energy. If I pronounce any of the words weird, just let me know, throw something at me. But that's their device. That's a stellarator. Looks awesome, right? It's got all those pumps. Those are for cooling fields. That stuff in the middle is magnets. They're going to ignite plasma, and then we'll feed it stuff, and it'll fuse, and we'll make heat, and we'll make steam, and all that. But that is there a man on there? It's a pretty good size. I think the fusion diameter of that one is somewhere in the 10 to 15 feet, and that total device is probably 30 feet wide, give or take. We've got, if you're physically on site, we set up some scaffolding, had a 1-to-1 scale and printed and hung up just to see what it looks like, and it still looks kind of small. But this is the first device. This is Infinity 1, not 2. This is how we're going to prove all those physics that we have not seen actually happen yet. There exist in models, but not in reality. And this is bringing it to reality. So this is what they're developing, stellarators using supercomputers. Oak Ridge has got a really good one on their campus. It's one of the top ones in the world, depending on what year it is. Just down the road, the University of Tennessee Knoxville Computer Science program keeps the supercomputer list for the world. Advanced manufacturing. The shapes of these things, if you look into the magnets, whenever we get to some of the other pictures, they're weird. They're all over the place. They're not traditionally machined parts. They're going to be shapes and materials that we don't use today. So advanced manufacturing is going to be important. You can't just, you got a drawing, cut a couple of pieces, bolt them together later. It's going to be a high impact environment with different materials. Nope, go back. We're not to stars yet. The bottom part, that says built for the people of the United States behind them. You can kind of make it out. That's our governor, Type 1 Energy CEO, and our CEO lined up there. Lobby at Bull Run. We were building these back then. It was technical report, I think number 38 or something, published in '67. All federal projects. You could call Congress up and order a complete book about yay thick that's got everything about Bull Run in it. Equipment choices, letters from the president when we were initiating the project. Same lobby, still, you know, advancing technology today at that same site.
Is that a Department of Energy project?
We were our own agency, but they were heavily involved. It was Department of Power for TVA then. A lot of history there of us being in and out of different, we're not the traditional federal agency, we're a small federal agency with a charter, so slightly different.
So it's a TVA.
TVA project. That picture, September of 2025, that's when we signed a letter of intent with Type 1 Energy for the first fusion power plant. So that's Infinity 2. That's the thing, you know, we're here to talk about today that's making the news, but that's the 350 megawatt electric equivalent plant and the agreement to do that based on the outcome of Infinity 1. All right, what is fusion? Power stars. Stars fuse things. Small elements combine, larger energy. You know, it's what's happening in the center of the sun. Those numbers are for the sun. I don't think we intend to hit quite those pressures, but maybe hotter temperatures. There's all sorts of interesting ways to go about it, but the plasma physicists swear that the equation for fusion is hot enough, close enough, and long enough. So if you get anything hot enough, keep it close enough for long enough, it will eventually fuse, is the idea. And when it fuses, it releases energy. So that's kind of the bare bones minimum. I did try to look up the electrical equivalent of the sun with those numbers to see if I could get an AI output, you know, based on how many tons of helium or hydrogen it fused a second. And AI says it's 386 million trillion megawatts, which is 300,000 years of the energy's Earth usage per second. So, I mean, obviously fusion's got quite a bit of potential, but it's still a fuel source and energy that we're making heat to make steam to, you know, turn a turbine. Because it turns out that water's a really handy material when you talk about specific energy and what it does at temperatures to go from, you know, liquid to gas. This is the pieces, right? So what are we actually thinking about using? Deuterium and tritium, elemental stuff. Smash a couple of those guys together in that hot enough, long enough environment, you get energy out. Energy out's heat. Just always think heat. You burn coal, you've got a chemical reaction, you get heat. You burn gas, you know, hydrocarbons, same thing, you get heat. That's the idea here, and they, you know, spit off a neutron and some helium, and that is why fusion's really one of those interesting long-term things. Is I don't have the processed uranium down to the fuel pellets, and I don't have to deal with the waste long-term. So if I can get, you know, relatively inexpensive fuel, which it should be with those elements. Tritium's very expensive, but these machines can produce their own tritium after you get the initial load started. You know, that's the advantage. I don't have all this extra stuff to manage long-term waste. It's effectively, you know, lower half-life, low-level waste that you don't have to put in cask and find a place for. So that's the goal. So save, clean, abundant energy, minimal inputs. That's all the idea, get more efficient over time with how we can generate electricity.
So this isn't the prototype?
Not yet. We're building it today. So it's to prove all of our physics papers work for Type 1 Energy, and this is where it started. So we've got fusion devices at Lawrence Livermore Ignition, National Ignition facility. They were the ones that had the big break-even power announcement about 2 years ago now. Everything from, you know, that break-even is, in theory, improving fuel density, plasma temperatures, plasma confinement. Close enough, hot enough, right? So all those pieces and parts keep advancing. So it's building better devices, engineering. I mean, has anyone done any looks at some of the very first steam turbines from way back when? They were tiny. They don't work very well. They broke a lot. Better, better, better. We got hotter and hotter steam. We've got better materials, you know. All the boilers were getting up to 3,000 PSI. We're getting supercritical. Efficiency improved, capability improved, materials improved. It's kind of what we're seeing in the same industry over time. One thing I really like about naming conventions, you can tell when the scientists and engineers are involved and then when it starts to become more commercial. HSX, that is helically symmetric experiment. W7X is a German word. I think it's Wendelstein. I'm not certain of that pronunciation, but it's a place. 7th design, X for experimental, right? Then Infinity One, it's more commercial, right? It's a name device, but all of these stellarator technologies were advancing over time. You got HSX was at University of Wisconsin-Madison. W7X was after that in 2016. It's advanced every step, and if you start to look up fusion reactions across all the technologies, because stellarators is just one, there's multiples, and we kind of hope any of them succeed. But they get longer and longer with plasma, right? So they've held longer and longer reaction times. They're more stable, they're more repeatable, they're cheaper. Every kind of step gets a little closer to, hey, this is something we can build a bunch of. All right, now let's talk about Project Infinity at boron. So we got all the pieces, let's bring them back together. This is the path to commercial fusion for type 1 energy, which is, you know, one stellarator option. Everything about this is, the goal is to eventually put megawatts into our system at that site. And again, regional partnerships, state support, technical support, Oak Ridge, universities, TVA. We're in this together to make this goal happen. So there's another good picture of the stellarator with all that magnet geometry inside. So the one on the left is Infinity One, that's the test. So you see there, advanced stellarator, test bed, long-term learning platform. If we need, you know, 40 PhDs to operate this thing, it's never going to work commercially, right? You can't get that many people to do that many places. So training testbed means, how do we train operators? How do we train technicians? How do we have the guys that need to actually work on this, work on it later? So validate the physics, but then keep using it to, you know, train everyone else on how this works, how to use it. Infinity 2. 350 megawatt electrical equivalency. So that is 350 megawatts of electrical output is the goal. That's kind of what the steam turbine would be sized for, which indicates probably 1,000 megawatts or so thermal load if Carnot is still to be believed. But effectively use the heat machine, you make the steam, and then it looks like balance of plant for a combined cycle unit or something. Steam coming out of the heat exchanger, I've got tubes, turbines, stop valves, I've got all the pieces and parts, spin the generator with that turbine and, you know, send it back to a condenser and run it through again. So it's very much going to look like, you know, a different heat source for a traditional steam-fired power plant technology, because steam is really great. Been using it for a very long time. It does a great job. It's dispatchable, it's reasonable. It's something we know how to work with. So it's you swap out the heat source. We know how to do the rest of it pretty well. This next part's brand new. I think the press release was mid last week. I had to send the slide through IP review before we could even put it in. Point it that way. Nope, went too far. This is forged PFC. Again with the acronyms. facility ongoing research, gas-cooled, energy dissipation, and plasma-facing components. The important thing for this slide is, you see the picture of the Earth up there? There's a bunch of these types of facilities in the European areas for scientific research. There's not really any here. So this is going to be a new facility we install at Bull Run, kind of the 3D mock-up in the left lower corner there. It'll be the first place that has the capability to test what happens when you make plasma-facing components very, very hot. That's the high heat portion. We need new engineering materials and capabilities for a lot of the fusion work to make it really commercially viable and easy to maintain and replace. Get those long runs that that utilities expect. We're going to do that at Bull Run. Once again, it's a DOE grant out. It's going to be built in a partnership with UT Knoxville, Oak Ridge, TVA site, Department of Energy, Type 1 Energy, all of those things together in that region to have these capabilities. And it's not just for this project, it's for anyone that needs that scientific capability in the region from the lab or elsewhere that can schedule time once we get the initial thing going. So it's got capabilities there on the right, a couple of E-beams, vacuum vessels, layouts. It's going to be state of the art. It's going to have a laser that's got all kinds of cooling capabilities that you can throw at materials. It's just that commitment of all the parties in the region to keep advancing technology towards fusion. And now you guys and everyone else, what do we need? Everything. Literally everything. So every version of engineer, some of my comms guys go, what's a cryogenic engineer? I go, it's a mechanical engineer that knows heat transfer better than the rest of us. There's going to be a lot of liquid helium and things like that associated with these. Material scientists, analysts. But for any of those guys, thoughts to come forward, you've got all the operation mission support, supply chain logistics, project management, safety, legal. This thing's going to look like an industrial power plant, kind of build site at first, but a lot slower. Who gets frustrated with schedules, right? When things change. Well, it's the first time you do something, we're going to have to be a little flexible in understanding when we come up on something, it's not discovery. Oh no, this thing that we were supposed to use was cracked. Now it's, we're going to have to completely redesign this part because we put it in, it didn't work like we expected. We're avoiding a lot of that with 3D modeling and some of the supercomputer work, but first of a kind is harder, right? And that's why it's important to do somewhere that's got that kind of support. All your options there for positions developed for operations and mission support. So what roles do you have operating a fusion plant that are different? Obviously the steam cycle, we all know what those operators are going to look like. It'll be real similar to what we do today, but how do you certify a guy to be a stellarator fusion operator that's got multiple million degrees machine in his hands? How do you monitor it? How do you maintain it? So power plant construction and ops, superintendents, fitters, welders, construction workers. We'll need literally everything. Every part of the trades and labor is going to be important. TVA obviously has been a strong union supporter over our history. We've got trades and labor support for every craft imaginable as we're building our sites. And we expect to develop what materials and means and methods we need. Power plants started out for us, in the 30s building dams, and then we built coal plants in the 50s and gas plants in the 70s. Well, 80s, 90s, nuclear plants in the 70s. Through time, we've continued to advance what we're capable of generating power with, and this is just a continuation of that. What's new, what's next, and how do we continue to repeat it over time? And I think that gets me to the question section with a fair amount of time left. I think 20 minutes.
We've got tons of questions, too.
Let me just clear your mic.
Spot. So again, we've got, you know, the angle. Raise your hand, and we'll take live questions, but we got a fair amount of them in the app. First of all, what is TVA's expected schedule for site development, major equipment procurement, and workforce mod? Now, I stepped out for a quick bio break. You may have covered it. Forgive me if I did. But any more detail on schedule, site development, equipment procurement particularly?
Procurement, no. We've got to finish the designs, right? So we're still, this is the plasma physics. They've got some early design work that I can't share absolutely anything about right now. But as soon as we zero in on those, start understanding how to construct the parts, because some of them just don't exist yet. They aren't finalized. We don't even know if they can be machined in some cases. We'll advance that with POLO RFPs when we get to the point of the power plant. Test device, we're going to probably leverage some of our power services shop in Muscle Shoals. We've talked to them about what their capabilities are as far as work there. So it's a developing process to figure this out as the design continues to go forward.
What new approaches have you folks implemented on this particular initiative that are new to the TVA protocol?
New to the TVA, that's an interesting question. It's really repurposing a coal site for something that's not our own existing technology, right? So this is seeing an example of a place that we can take a asset that served us well for 56 years, I believe Bull Run was in service, and advance those components forward for new technology understanding. That's the different thing here. We've repurposed coal and gas sites all over the place, but a lot of times that means, knock it down or find another piece of the property that we can put a gas plant up and, show the coal plant and move on. This is keeping up with the actual structure of the Bull Run fossil unit into the synchronous condenser, into fusion, researching an energy complex, really. So what can we do that's more than just one fuel source or one energy type at a site? So that's, I think, a little wider energy complex thinking allows us to do more with the same footprints.
Excellent. Are you collaborating with other mega projects, particularly with Duke, Southern Company, Florida Power and Light? Is there a collaborative given limited workforce availability?
Currently,
By
no.
the way, all those people are here.
Plenty of discussions, nothing I can currently say.
Okay, good. We can make that happen, Andrew, if you like. So, just saying. All right. How will constructability be validated given the novel HTS magnet system and the stellarator geometry? How will constructability be validated?
Very carefully.
We hope.
That is one of TVA's goals as a utility influence with the Type 1 Energy. As a company, they're working on the technology, they're working on the science. We want to be the voice of reason in the room with everyone else. Now, there'll be real, professional engineering firms associated with this. There'll be others, but we're a utility. Who else builds billion-ish dollar projects that's not a utility or, some other petrochemical industry with real regularity, right? That's everything you get for a power plant's a bill and a half nowadays. So taking those knowledge sets, looking at this and saying, I don't know how I could do that, and having those discussions with this company early on and hopefully to influence some of those designs, we think can really help long-term constructability, especially if you've got a fusion island that is very much their part and then a power island that is very much traditional for us. We'll know exactly how to do that power island, and then we can help with the fusion island, understanding how to connect the two together.
Excellent. I think we have a question over here, Andrew. Rob, go ahead.
Yeah, it's Rob Wagner, Procter & Gamble. Question is with this brand new technology, what rules and regulations are required to follow? What changes are you asking for? and what do you need to do? Because I think of the building construction industry, we are always, building codes come in, and when we made Astrodome, we had to change all the rules for construction to build an Astrodome, for example.
So I can't remember all the numbers off the top of my head, but the CFR subsections on nuclear power versus nuclear sources, I do believe that this will not be covered under the same power plant regulations as the nuclear power plants. It'll be a slightly lighter version because there's not as much risk associated with it. Most likely will come down to state regulation, and Tennessee obviously would have to be one of the first states to undertake this. There was a permit application filed by Type 1 Energy not long ago for their first bit of work. There's a few press releases on it, and how we get to those regulations, they don't exist, right? We got to figure them out.
I think maybe hidden in there was a follow-up question, but what is the timeline for these regulatory and licensing compliance issues? What are the current timelines anyway?
Type 1's got a few stated goals. I'm just going to talk broadly that we've got some initial construction to begin in the next, well, the Forge PFC a little earlier than the others because it's a known technology. But the idea is Infinity 1 to come around in the late 20s. So I think 28, 29, something like that, with the start of Infinity 2, the actual power plant, with the ability to bring power to the grid in the 2030s. And you know how far we get with Infinity 1 depends on when Infinity 2 lands. I'm not going to speak for the company and how far they are on their designs, but you know, as long as we see progress towards the goal, we're there to support it.
Questions from the floor? Here's one right here. Let's take one right here from the floor. That we've got about half a dozen here on the app. Go ahead, sir.
Thank you. I'm Andrew Zukowski with Join. I'm just curious, has TVA been this closely involved in first of its kind development of new generation technologies in the past, and how does this one differ?
Recent past, no. This is a little new. Innovation is part of our charter, though. So back to the fertilizer, the whole reason that was in the deck is we have done new technology development in our history. Innovation of new technologies and how we can use those to bring up the people of the region is part of our core mission. So it's always been a thread. Just how close to the front it is changed over time.
How will the manufacturing and supply chain strategy for core components, especially HTS magnets and modular assemblies, how will those be structured between TVA's power service shops and new vendors?
Don't know yet.
Fair question.
Yeah, just don't have an answer. But yeah, it's with any new piece and part, we've got to figure out what it is and then who can make it. So
yeah.
I'm sure we will advance those as we have clarity on what we're looking to build.
What are the site prep and infrastructure scope requirements for transforming the retired Bull Run site into the fusion power complex, including utilities or heavy lifts and civil works? What are the site preparation and infrastructure scope requirements for all that?
Well, that's the good news is it looks a lot like a coal plant. So those requirements are going to be very similar to the supercritical coal unit we had there. We've obviously been bringing down the unneeded structures at that plant, but it's going to be flat land, cooling water is a possibility. We don't know if it's air cooled or water cooled at this point, but the grid connections, all the parts look just like a coal plant, short of the actual shielding for the device for the fusion. And those are being developed now, but very similar to traditional coal plant infrastructure technologies, and then a little bit of the radiation shielding.
Hiring is at a fevered pitch for CMs and CEs around the country. What is your hiring of new talent look like given this project scope?
For us, nothing different yet. Right, we've got a few years out until major construction would be a thing at the site, so we need to see Infinity 1, which the company is handling. They are hiring feverishly. I think when I started, there were about a half a dozen of them. Now it's in the triple digits. I'm not sure exactly where. And that's been the last 18 months or so. They've hired a lot of that, but it's, you know, all walks and fields. So I can go to their office and talk to a guy that is one of the original physics guys that developed the technology early. PhD, been around forever. Then there'd be a brand new person that's got a construction management degree working on schedule optimization and theories for them 3 cubes over. So they're, you know, all over the place, and they're thinking about the total life cycle of this build as they're developing it, which is one of the reasons I think it could be very successful long term, is they're seeing more than just I made plasma, I made heat, y'all do something with it. They're looking at the whole pieces and parts to get it to be effective.
Are you using collaborative design and construction with co-location space? And what is the project delivery model? EPC question? Assuming it's separated to core and shell versus the technical aspect in some way. I'm going to repeat that, and that'll give you time to cognate on it and me time to get my words right. How's that? Are you using collaborative design and construction with a co-location space? And what is the project delivery model? Let's stop there. We'll take this into segments.
Yeah, so project delivery model, I would say, is not set yet. Assume there will definitely be an E, a P, and a C, but whether or not it's the same company's going to be a question for the first of a kind just because of how complex it is. Right, traditionally you hire an EPC to shovel risk off, right? So you've sold a little bit of risk for a little bit of profit and moved on with your day. I'm not sure if that's the right case here. I'm sure we'll have a lot of collaboration between those groups, but it's going to have to be flexible and slightly different because of that. You know, site delivery and things like that, we have not gotten that close yet to hammer all those out, but they're part of the DNA of how they're developing it so that we can issue, you know, a standard work breakdown structure package to somebody later. There's going to be the theory that, hey, build this for me, build that for me. Maybe this part we get from a traditional vendor that's done boilers. This is a traditional turbine vendor, but this is a completely different vendor. So I think it'll be broken out a little bit, and we'll probably see multiple options, but we just don't know yet.
So what is the best source of information for new news concerning this massive project?
Our press room, as always. You know, anything that's involving us that is part of it will come through our TVA newsroom. It's on the website. You can find it pretty easy, TVA.com. Type 1 Energy, Oak Ridge National Lab, University of Tennessee, Knoxville. So those
I notice
guys,
you're always plugging UT Knoxville. As a UK Wildcats fan, I got some trouble with it. And how did UT Knoxville do last night?
well, last night was fine. When we played you guys a few weeks ago in Thompson Bowling, it was not nearly as good.
A note to self: don't poke your speaker in the eye when they're talking. Oh God, I'm just having some fun with you, Andrew. I think we got a question here. Thank you, Paige. Yes, sir.
Yeah, hey, thank you, Andrew, for your presentation. Super informative. I wonder if TVA has any targets or if Andrew has just a personal opinion on, say, the next 5, maybe to 10 years of total added power generation from TVA. What percentage of that might be applicable to the AI data center?
We've got a draft IRP out, and I'd have to refer you there. So that draft IRP's got many versions of the future. There's tranches of load growth. I don't know all those numbers off the top of my head, but it breaks it down by both energy type and quantity. So you can see, you know, what's capacity versus energy outlays, what different technologies serve those roles for us, and how they might fit in our system as a whole.
One final question. What other obstacles outside of labor and material lead times, Andrew, does the power industry experience that other markets may not have to deal with? Any thought on that? What other obstacles outside of labor and material?
Who goes out and buys more megawatts just so you have them later? Right? It is very much a demand-based thing. Everybody wants to buy less of our product. So we have to take an uncertain future with uncertain inputs, make 20 or 30-year asset decisions, and hope they all work out, right? So if you're looking at how long-term you plan to deploy large assets like this, it's a really hard question on what blend assets do I need, how do I weave them all together, what decisions today are going to look like we were geniuses in 30 years and which ones are going to look foolish. Probably going to make some of both. It just happens because the future's hard. If we were perfect at predicting it, none of us would be doing this, right?
Good. Well, let's. We do have another question. Where am I looking? Can't see for the lights, but I see motion. Go ahead.
I'm just curious, do you think we'll be able to use and market the helium byproduct off fusion reactor? There's been a helium shortage, among other things, reported in the last few years.
It's a great question. I have no idea how easily it would be harvested or not, or if it would go, back into the plasma reactor. It's a question I have no idea the answer of. I'm going to ask them when I get back, though.
That's your Southern Company colleague over there, by the way.
It's all good.
Appreciate it. Great question. Any final questions? I see Andrew disappeared. Is there no final questions? If not, let's show our speaker a great round of applause for a very informative session.
Thank you.